Hello everybody, my name is Pablo Zapata, and within this short and informational video, I will state the basis of my candidature and present the main objectives of my project for the Caixa PhD fellowship. In my recent research activity, as well as in my master's studies, I have been focused in two main different topics. On the one hand, the conception, simulation, and manufacturing processes of radio frequency devices such as antennas, filters, absorbers, or attenuators, especially at microwave frequencies. On the other hand, the study of optimization techniques like meta-heuristics or genetic algorithms and their applications to problems like network planning or energy efficiency techniques. Well, the main goal of this project is to merge these two areas of expertise, taking advantage of the knowledge in the optimization domain to improve the design and manufacturing processes of radio frequency devices using technologies like 3D printing or meta-surfaces. And now, let's get a bit more into detail and see a couple of examples of this idea.
Meta-surfaces can be defined as a sort of antenna formed by a two-dimensional distribution of emitters. While 3D printing doesn't only make manufacturing cheaper and easier, but also allows for the introduction of new and promising materials like graphene or charged polymers. This can be applied to create tunable radio frequency components or low-cost testing and measurement equipment, but also it can be used for applications like radar or satellite communication or the promising radio frequency imaging. In this example, the working principle of RF imaging is shortly summarized and illustrated. While different kinds of emitters form a metastructure that correspond to the black and white squares on the picture. They emit several waves that form a global radiation pattern. By changing the configuration of the metastructure appropriately, which is done with the help of an optimization engine, we can perform the detection of hidden objects by RF imaging. In this example, the emitted electromagnetic waves pass through the wall and are reflected from the hidden bottle. The reflected waves are captured by a receiving antenna, and after a post-processing phase carried on in the computer on the right, the bottle is reconstructed. This same principle could be used for other applications like medical diagnosis, sensing, or material characterization. However, the engineering process of these devices is quite complex, and a large number of varying factors must be taken into account. Here is when optimization comes to play. Despite most simulation tools like CST, Microwave Studio, or MATLAB do have optimization engines, they are canonical implementation of existing algorithms that do not incorporate problem-specific information into the search. As you can see in these two examples, minor changes in the device structure or characteristics can result in a huge impact of its performance. While here, problem-specific search operators like recombination, mutation, or selection can be applied to hybrid meta-heuristics, genetic algorithms, or artificial intelligence to move one step forward from these predefined optimizers implemented in those simulation tools. Moreover, the performance of the optimization process can be boosted by the use of GPUs and parallelization techniques. In this example, a master-worker architecture is showed, in which several workers are connected in an adaptive way to contribute to the evaluation of the solutions generated by the genetic algorithms located at the master. This reduces considerably the computing time, making it possible to perform faster and more complex optimizations. It is worth it to mention that this approach can be implemented together with multiple techniques like hybrid meta-heuristics or artificial intelligence, including machine learning or neural networks. Moreover, it can be used in a wide range of domains and applications. For example, these technologies are meant to play a key role in the deployments of future 5 and 6G networks, helping for an enhanced routing and a better user quality of experience, and improving the energy efficiency.
In conclusion, the incorporation of advanced optimization techniques to the domain of radio frequency device manufacturing could result in very useful tools that can make big research contributions in both domains. Moreover, the interdisciplinary character of the project makes it really flexible, being able to apply it to multiple domains and build solutions both for academical and industrial third parties.